Students, parents, teachers, and all lovers of knowledge. On behalf of the production crew and the entire management of Oxygen 96.9 FM, broadcasting live from the Knowledge Hub, 121-123 Obafemi Awolowo Way, Okeado, Ibadan. On this note, I welcome you all to class on air physics. I am SHEU AZEEZ, your host on this program. Today, we are starting right from the beginning with the topic physical quantities. Things we measure in physics are height, time it takes to move from Okeado to Mokola, the temperature of Ibadan today, distance from Malete to Gate, that's the length, a bag of rice, that's the mass, and so on, are physical quantities. Physical quantities. Under the physical quantity, we are going to know the definition of physical quantity, as I've said in my introduction. And we are going to be dealing with all these subtopics under physical quantities. We have fundamental and derived physical quantity. The second aspect will be scalar and vector physical quantities. And the last, under the topic for today, is dimensional and dimensionless physical quantities. As I've said earlier, what we measure, how we measure it, the units we measure it in are the foundation of every physical law. But in a simple term, let me tell you this: anything that is not physical should not be called physics. And here we are going to start with the first aspect of the physical quantities, so which is a fundamental and derived quantity. Don't forget, I mentioned under the definition for physical quantity, I said if you can measure and give it a numerical value and unit, so that means you've done physics. So these two things go hand in hand: the numerical value and the unit. So the numerical value is the magnitude, while the unit tells us what exactly we are measuring. Give for example, so let's say we have 5, somebody just say okay, 5.2. 5.2 mean nothing until we are going to we are able to distinguish it with unit. So is it 5.2 goats? Is it 5.2 cup of water? So now the unit will tell what exactly we are measuring. So that means if we now have 5.2 kilogram, so that means 5.2 is the numerical value and the kilogram is the unit. So now we can now vividly tell that we can have some other examples like 5 inches, we can have 3 kilometers, and so on and so forth like that. So the first aspect of the physical quantity is fundamental quantity, and these are basic quantities used to define all other quantities, and it is the base. Nothing can be used to define it, while the unit now be the unit upon that other quantities unit depends. So that's the definition for the fundamental quantities and basic quantities. In some texts, you can see basic as base. It's still the same thing. Some texts recognize it as primary. Sometimes they recognize it as foundation. So the word is still they are nearest in meaning. They can be used interchangeably. So now, examples of fundamental quantities. I would like my listeners to put it down in a table. So just have a table that have 3 columns. The first title of the first column is quantity. The next column, the middle column will be unit, and the last column will be unit symbol. The first of all is length. That means under quantity, you put length. Just write down the length there. And when you are talking about the length, the unit of length is meter. So meter spell METRA, meter. And the unit symbol is represented by the lowercase m. That's the first. Number 2, we have mass. Under quantity, just write mass there. Under units, it is measured in kilogram. That's the standard unit of measurement. And mind you, you've done that since your primary school, and this one is even like primary school work. So that's why I said physics is physical. So you have been doing it. Anything you are doing daily, you are still doing physics. So SI unit, it is the international standard system of units, and then it's derived from the word for the French word called le système international de l'unité. So now the unit is a kilogram, and the symbol for the unit will now be uppercase K and lowercase g. That means kg. The K will be uppercase, while the G will be lowercase. The third fundamental quantity that I'm going to mention today is time. Time. So we are still coming back to that later when we get to measurement, but that will be for another class. So time, under unit, seconds, SECOND, second. So and then for the symbol is lowercase s. The next quantity is electric current. In some texts, you can see it as only current. And then this one, the unit is ampere. The unit is ampere. And ampere goes thus: AMPERE. That's ampere. And then the unit symbol. So you can have it in 2 ways. The first one is uppercase A to represent ampere, to denote ampere. Or in some text, you can see it as uppercase A, lowercase m and lowercase p. Amp. So it can still be recognized as the symbol for electric current. So the next one, which is number 5. Number 5 now is temperature. And the temperature, the standard unit of measurement of temperature, under the unit, you put Kelvin. Kelvin is Kelvin. Kelvin. And the unit symbol is uppercase K. That means K in uppercase. So let's now go to the next one, number 6. Amount of substance. That means measurement of substance. So I think you'll be hearing that when you get to chemistry, or you'll be hearing that from your chemistry, amount of substance. So now, and the unit of measurement of that is mole. And that mole goes thus: M-O-L-E, mole. And then the unit symbol is M-O-L, all in lowercase, M-O-L. And the last here is number 7, which is a luminous intensity. In some texts, you will see it as only intensity, luminous intensity. And this one is measured in candela units. So that means C-A-N-D-E-L-A, candela. And the symbol is CD. So that means lowercase c and lowercase d, CD. So that's the unit for what is it called? Unit for luminous intensity unit. That means symbol for candela, unit of luminous intensity. So now, if you look at it in all, you will see that we have 7 basic, or we call it independent, physical quantity, and then they are all constant throughout the whole world. Okay, let's now move on to the second leg of the first aspect of physical quantity. You know, I said we are going to be discussing about fundamental and derived quantities. So now, before we move on there, let me quickly run on the first aspect, which is a basic, or we call it fundamental, or we call it primary, or we call it foundation quantities. We have length, we have mass, we have time, we have electric current, we have temperature, we have amount of substance, and then we have luminous intensity. Let's now go to the second leg, which is derived quantities. So under derived quantity is just those quantities that are obtained by simple definition, right? That are obtained by some simple combination of fundamental quantity. So, and then when we mean simple combination, we mean by maybe by addition, multiplication, subtraction, or division. So now, and first example there, example of derived quantities. So we have the first example there, we have area. So that one too, I would like us to draw a table for that too, for the example, so that it will look compact. So now, the 3 column of table. So the first column, let it be quantity. The next column, let it be derivative or derivation, anyone. And the last column, let it be symbol of units. Now the first, Under that, the simplest that we can have under derived quantity, the simplest example is area. And you know that area is length times breadth. That's a simple formula from your mathematics. Length times breadth. So now, and then you know length, breadth and length, they are from the same family. We can say length and length. The only thing is just that to distinguish where this length belong and where the other length belong. So now, and we know that the unit of length right from the fundamental quantity is what? Meter, m. So that means it will now give us m times m. That means the first length, which is length, is m, and the unit of the second length, which is breadth, is m. So it will now be, and then from your law of indices, you can remember that. I think you've done that in mathematics just this Tuesday. So now that one is the first m is carrying is raised to power 1, the second m raised to power 1, and when you are having a multiplicative law of indices, so you are going to pick one of the base and add the indices or the powers. So now it will now be m raised to power 1 plus 1, which is m squared. So and then we call it meter square in physics. So now the second one is volume. Volume is length times breadth times height. So all are in the family of length. We can say length times length times length. So and that one will now be m times m times m. So apply the same rule, we have meter cube. So or cubic meter. So now the next one is speed. Speed, you've known that from your motion, even right from your primary school, that speed is represented by the formula distance over time. That means distance divided by time. And you know the distance is in the family of length. So and then that one has unit m, and the time unit s, which is second. So now that means now be meter per second. So and then the acceleration. So the acceleration is velocity divided by time. That's the derivation. Velocity divided by time. And you know velocity is meter per seconds already, and we still have another per seconds. It now be meter per seconds, which is meter per seconds square. Now the next one is force. Force is mass times acceleration. So we have it in Newton. That's popular unit, but we can still break it down. We are still coming back to that when we get to our dimensional analysis. So now we can have it as a kilogram meter per second square. So because mass is in kilogram and acceleration is meter per second square, so we can have it as another unit, which is even standard unit as well for force. So and then the next one there is density. We have density to be mass over volume. So that one you will have be kilogram per meter cube. So that we know that what is it called? Volume is meter cube or cubic meter. So and then mass is in kilogram. So it will now be kilogram per cubic meter or per meter cube. Anyone. So now the next one is velocity. So there is a relationship between velocity and speed. So but what differentiates them? So we'll still come back to it in the next subtopic under physical quantity. So we have velocity, we have work or energy. You can call it work or you call it energy. So that one is force and distance. So and that one is in joule. So and then when you are saying you want to give it in another unit. So now be Newton meter. We have power, we have moment. So let's go to the second leg of physical quantities, which is scalar and vector quantities. Scalar and vector quantities. Now, when we want to define vector, scalars. Let's start with scalar. Scalar quantity. Scalar, let me spell scalar for you. So S-C-A-L-A-R, scalar. Or some pronounce it scalar. So I don't know. So but scalar will be very better. So now scalar physical quantities are quantities that have only magnitude. They have only magnitude. So that means they possess only magnitude. So, but vector quantity, by definition, are quantity that have both magnitude and direction. So that means if you are talking about scalar now, scalar has only size. So you can just measure it in size. There is no specific direction. But we are talking about vectors. Vectors are quantity that they will have both size and specify direction. So now let's now take a look at examples. So for scalar quantities, so examples are mass, temperature, energy, time, speed, distance. And I think I'm too fast. So let me come again. So the examples of scalar quantities. So we have mass, we have temperature, we have energy, we have time, we have speed, we have distance. So now let's now go for example of vector quantity. So that means those ones that have both magnitude and direction. So we have displacement. That's the first example. Displacement. Next example, velocity. Velocity. The next example is acceleration. The next example is force. The next example is momentum. And another example is weight. So we still have countless of examples for both, but for the purpose of this class, I would not like to bore you with that. But let's see. Let me give you one direction to this particular vector and scalar. So when you look at acceleration, you can see that acceleration is velocity over time, velocity divided by time. But you can see that time is scalar, while velocity is vector. So is because of that velocity that makes acceleration a vector quantity, and the same thing goes for force. You know, force is ma, mass times acceleration. So now let's now go to differences between scalar and vector quantities. So I would like you to put that one in a table 2. The first distinguishable factor for scalar and vector physical quantities is you can use definition. When you are asked to differentiate, to distinguish between two quantities in physics, you can use their definition, you can use their formula. That means if they have one. So you can use their units and so on like that. So now let's now go to the first one here. So right, under scalar quantity, put it in a table 2. So that means it will be 2 column. The first column title is scalar quantities, while the second column title is a vector quantity. Now, under scalar quantity, it has only magnitude. That's from the definition, right? And under vector quantity, it has both magnitude and direction. That's the first distinguishable factor. So let's now go to the second one. It's change by change of their magnitude. That means that's for scalar. Scalar change by change of their magnitude. By change of their magnitude. So let's now go under vector. Vector change by change of either magnitude or direction or both. So that means if the magnitude change in vector quantity, it's change. The quantity change. So that means if the magnitude remain the same and only direction change, so that means the vector quantity change. And if both change, it still affects the vector quantity. It will change. So now the third one is that under scalar quantity, they are added or subtracted by laws of ordinary algebra. They are added or subtracted by laws of ordinary algebra. So now this is just addition, simple addition and subtraction. So what this one means is that when you have a quantity that have magnitude of 2, maybe let's use units, general units, 2 units, and you have another quantity, the same scalar quantity that have of a magnitude 5 units. So automatically, if you want to solve it, it's either you deduct one from the other or you add both together, depending on what you are asked to do. So now that means if you are to add, so 2 plus 5 is 7 units. And then if you are to subtract, so 5 take away 2 is 3 units. So let's now go to under vector quantity. These are added or subtracted by laws of vector algebra. So this one, I will not be able to go deep on it for today's class because vector on its own is a topic in physics. So now, let me just explain like this. So majority of you will have had that during your junior classes, that the laws of vector algebra is 2. The first one is law, what is it called? Triangular law of vector. The second one is a parallelogram law of vector. So we are still coming back to that later. Don't let me bore you with that. So now, welcome back. Before we go to the next items, which is dimensional and dimensionless physical quantities. So let's take a look at SI unit preface. So what is the reason for these prefaces? The reason is just when we have micro or macro magnitude, or let's say number. Let me use number so that I will not be taking you back to where we are coming from. So now number. So now, and we don't want the unit to change its status. So automatically we come around with this preface. And then you know from your English, you know suffix, you know preface. So that means preface is afterward, while suffix is before the word, before the main word. So now, this prefix, we use it in physics and mathematics to just bring macro numbers. If I mean macro, macro means big, very big number. And micro, which is a very small number. So I think during the primary school days, you use standard form for that. That's what you learn under standard form. So now, we now have some examples. If the unit remains as it is, it will be multiplied by 10 raised to power 0. So, and then you've learned that from your law of indices. Anything that raised to power 0 is 1. Any number raised to power 0 is 1. 1 million raised to power 0, 1. AZEEZ raised to power 0, 1. If I'm a number. So now, we now have 10 raised to power of 3. That means 1,000. So if you now have that as multiplication factor for a prefix, so that one is called kilo. It's called kilo. And then it is represented by uppercase K. So that's why we have, when we have meter, when you have 10 meter, and you want to write it as the basic, it should now be 10 times 10 raised to power 0, which is still the same 10. So, but when it's now in thousands, so when you have 1 times 10 raised to power 3, that means you mean that 10 raised to power 3 is 1,000. So why, what is it called? The 1 is the base. And when you put it together, it will give you 1,000 meter. But instead of writing 1,000 meter because it's becoming big, you can write it as 1 times 10 raised to power 3 kilometer. So now, the next one is 10 raised to power 6. 10 raised to power 6 is called mega. So, and then it's represented by uppercase M. So that's why you see it when they are broadcasting on national grid, as in electricity supplied by the federal government from hydropower. So they said we are generating so megawatts. So that mega is times 10 raised to power 6 of watts. So now the next one is giga, which is 10 raised to power 9. And I think my student will understand this from their basic knowledge of ICT from their junior secondary school. So giga, so represented by uppercase G. So let's now go to micro. Those are macro. Micro, we have 10 raised to power minus 2. So which is a centi. So that means we have centimeter. From centimeter or centiliter. So that means you know that if you want to change it to meter or liter, you are going to divide it by 10 raised to power 2. So now, and then it is represented by lowercase c. So I think even for your sachet water, you will see it on it, 50 cl. So that means is times 10 raised to power of what you're supposed to get. Now, the next one is 10 raised to power minus 3, milli. And then it's represented by lowercase m. And then it's times 10 raised to power 3. So the next one is micro times 10 raised to power minus 6. So that one is represented by a symbol. That symbol, I believe that all of you will have seen it before under your law of friction. So that symbol is called mu. So it's like U, and the left leg will be longer than the right leg. It will grow leg. So now that's mu. It is called mu. It's a Greek letter. So and then the next one is nano times 10 raised to power minus 9. So which is represented by lowercase n. And we have another one, pico. Pico is times 10 raised to power minus 12. Another one is represented by lowercase n. P, sorry. Now, and then in practice, when we have 1 kilometer, just to reduce a bigger number, you all know that is 1,000 meter. So, and then if you have 1 milligram, so 0.001 gram. 1 milliseconds is equal to 0.001 seconds. So if you see all these derivatives, you know that we are using it to bring it closer to the number that is affordable to deal with. So that's the essence of what is it called? The essence of prefaces. Okay. For our students out there, will not be able to continue the last leg. We'll postpone that to next class. So because that one itself is a topic on its own, the dimensional and dimensionless physical quantities. Now, for what we have done so far, I think by now we'll be expecting call from my listener at home. And this is the studio line to call to 070-4700-3969. I take that again. 070-4700-3969. And another one, 070-4700-2969. Again, 070-4700-2969. Thank you. I'll be expecting your call. No? Okay. Now, as I'm awaiting your call, I want you to take note of this. Hello? Hello, good morning. Hello, caller. Okay. Sorry, I lost that. As I'm waiting for your call, at the beginning of this lesson, I told you that physics. Hello? Hello? Hello?
Hello?
Hello, good morning, sir.
Hello, good morning.
How has been your day, sir?
This is a great job.
Yes, sir.
And I believe our young ones will learn better from this.
Thank you, sir.
This is Mr. Lasisi.
Thank you, sir.
So I really appreciate the work. It's highly commendable.
Yes, sir.
So just to catch up with you and greet you on that and keep it up.
Any advice for improvement?
Oh, the work is perfect.
All right. Thank you.
There's still room for improvement.
Thank you. I appreciate that. We appreciate that. So now, okay. Thank you everyone for listening. All right. That's it for today on physical quantities. If you can measure it, you are doing physics. That's very simple. Don't forget to tune in for biology tomorrow, same time, same station. Thanks for tuning in to Oxygen FM, the station that inform, inspire, and ignite. I am SHEU AZEEZ. Join us next week as we talk about the dimensional and dimensionless physical quantity and measurement and instruments. Thank you.
Your heartbeat. Oxygen FM 96.9 Ibadan.